Wow. That downpour we had the other day and the wind just howling. It really makes you stop and think, doesn't it? What actually causes these huge, powerful storms?
It really does. And it gets into some pretty fascinating stuff happening up in the atmosphere.
Yeah.
So today, let's dive into that. We'll look at the core conditions, the ingredients, really, that kick off these intense storms.
Mm-hmm.
We've got some great insights, drawing from, general weather science concepts and also specifics from hurricane studies.
Okay, sounds good. So the mission is to figure out how these things form and I guess what makes them so
Yeah,
powerful.
exactly. What starts them, what fuels them.
All right, so first things first. When we talk about the atmosphere and what it's doing, what's the basic distinction we need to make? Weather versus...
Right. Good place to start. You got weather, which is, what's happening day to day. Is it raining now? What's the temperature? That sort of thing.
the immediate snapshot.
Yeah. And then climate is the bigger picture, the long-term pattern. Like, what's the typical weather for this place over years and years?
Okay, snapshot versus the whole movie. Got it. Now, hurricanes specifically. How do the guides define one? What makes a storm a hurricane?
Okay, so a hurricane is defined as this really large rotating storm system.
Mm-hmm.
Key things.
Mm-hmm.
It forms over warm tropical ocean waters, and it packs high winds and loads of rain.
And they don't just pop up any time, right? There's a season for them, especially in the Atlantic.
That's right. Officially, the Atlantic season runs June 1st to November 30th.
Quite a long window.
It is. But the real peak, when things are most active, is usually August through October.
And geographically, where do they tend to form? Always over water, you said.
Yep, warm ocean water is the key. Near the equator, typically. Think the Atlantic, the Gulf of Mexico, the Eastern Pacific. Those are the main breeding grounds.
Okay, warm water is the birthplace. So how does it start? How do you go from just ocean and air to this massive spinning storm?
It kicks off when warm, moist air rises from the ocean's surface. As that air goes up, it leaves behind an area of lower pressure near the surface.
Like a little vacuum.
Sort of, yeah. And that lower pressure pulls in more air from around it. That air also warms up over the water, picks up moisture, and rises.
And as it rises, it cools.
Exactly. It cools, and the water vapor it's carrying condenses. That's how you start getting clouds and eventually thunderstorms.
And there's a specific type of cloud that's really important here, isn't there? Mentioned in the hurricane info.
Oh, yes. Cumulonimbus clouds. Those really tall, dense, towering ones.
The thunderstorm cloud.
Those are the ones, they're like the building blocks for a hurricane. Absolutely essential.
It feels like dominoes falling. Warm, moist air rises, makes these huge clouds. Now, thinking about basic cloud formation, it's not just rising air, is it? There's more needed.
No, you're right. You absolutely need water vapor, obviously. And as that air rises and cools, it just can't hold as much vapor anymore. It gets saturated.
But full...
Right. And that excess vapor needs something to condense onto. It can't just become a droplet on its own.
Ah, right. Little particles.
Exactly. Tiny things floating around. Dust, pollen, salt from sea spray. These are called cloud condensation nuclei, or CCNs.
So the water vapor grabs onto these little specks.
Yep. That's how you get tiny water droplets, and enough of those make a cloud.
Huh. So you need seeds for clouds. That makes sense of that cloud seeding idea you hear about sometimes, trying to add those particles deliberately.
Precisely. Trying to give the condensation a nudge. So, okay, we've got these initial storms brewing. What turns them from just thunderstorms into something much bigger, much more powerful?
This seems crucial. The guides really stress warm ocean water, right? A specific temperature, even.
Yes. At least 26.5 degrees Celsius, which is about 80 Fahrenheit. That warm water, plus plenty of moisture in the air above it, that's the high-octane fuel.
Okay, so how does that fuel actually work? How does the warmth power it up?
Well, as more of that warm, moist air rises from the hot ocean surface, it keeps cooling, condensing, making more clouds way up high. And here's the kicker. When water vapor condenses into liquid water, it releases heat.
Latent heat.
Exactly. Latent heat. It's energy that was stored in the vapor. Releasing it warms the air around it.
Making it rise even more.
You got it. It becomes less dense, rises faster, which pulls in even more warm, moist air from the surface below. It's this self-feeding cycle. The storm literally runs on the heat released from condensing water vapor. And interestingly, the depth of that warm water matters too.
Oh, yeah. How so?
Well, if it's just a shallow layer, the storm's own winds can churn it up, mixing it with colder water from below, cutting off the fuel supply. But a deep layer of warm water can keep feeding the storm for much longer.
So deeper, warmer water means more potential power. Makes sense. And what if the water's too cold? Say, below that 80 Fahrenheit mark.
Then the storm just doesn't have the energy it needs. It either won't form at all, or if an existing storm moves over colder water, it'll weaken. Starve it of fuel, basically.
And the sun is behind all this ocean warmth in the first place, presumably.
Absolutely. The sun heats the ocean, that drives evaporation, putting the water vapor fuel into the air to begin with. It all starts with the sun.
Okay, so we've got the birth, the fuel. Now, inside a fully formed hurricane, what's going on? We hear about the eye.
Right, the eye is pretty unique. It's the calm center. Surprisingly calm, actually, with low pressure. But surrounding it is the eye wall.
And that's not calm.
Definitely not.
Oh.
That's where you find the strongest winds and the heaviest rain, the most intense part of the storm.
You mentioned evaporation, putting water vapor into the air. Just how much water are we talking about? It must be enormous.
Oh, it's staggering. The amount of water evaporated from the warm ocean surface is just immense. That's why hurricanes dump such incredible amounts of rain.
And I remember reading that high humidity and warm temperatures help the hurricane hold all that water. Why is that?
It's simple physics, really. Warmer air can physically hold more water vapor than colder air, significantly more. And high humidity just means the air is already close to its maximum capacity. So these warm, humid conditions let the storm carry huge amounts of moisture ready to be released as rain.
And then what brings it down? Just gravity.
Yep, good old gravity. When the water droplets in those clouds get big and heavy enough, gravity pulls them down. Precipitation.
Okay. Now going back to those little particles, the CCNs, you mentioned dust, pollen. But over the ocean, what's the main source?
Over the vast ocean, the primary source is sea salt from ocean spray.
Spray. How does that happen?
Just wind whipping across the waves. It kicks up tiny droplets of seawater. The water evaporates, leaving the salt crystal behind, floating in the air.
Huh. So the wind itself helps make the stuff needed for more rain. That's quite a loop.
It really is. More wind, more spray, more salt particles, more surfaces for condensation. It helps boost cloud formation and precipitation within the storm. It's a neat little feedback mechanism.
Okay, changing tack slightly. The guides mention hurricanes usually form from maritime tropical air masses. What's special about those?
Well, the name gives it away, really. Maritime means it forms over the ocean. Tropical means it forms in the tropics. So these air masses are naturally warm and absolutely loaded with moisture, the perfect starting ingredients.
Right, warm and wet. That makes me think. I saw a map showing hail frequency. Less hail out west, more in the middle of the U.S. Could the type of air mass, like maritime versus continental, explain things like that too, affecting other storms?
Oh, absolutely. That's a great connection to make.
Yeah.
Air mass properties are fundamental. Maritime air, whether it's warm tropical or cold polar, tends to be moist. Continental air, forming over land, is usually much drier.
So drier air inland.
Generally, yeah. And when different air masses meet, say, moist air from the Gulf meeting dry air over the plains that creates instability, big thunderstorms, sometimes hail. The lack of hail in places like Nevada, like the map showed, is likely due to being far inland, dominated by drier air. Geography matters.
Definitely seems key. Okay, back to hurricanes. When they finally hit land, what happens? What are the impacts?
They can be devastating. The study guides list the big ones. Massive flooding, both from the rain and the storm surge.
That's the ocean water pushed ashore.
Exactly. Then you have the incredibly strong winds causing damage, tearing things apart, power outages that can last ages, and just general destruction, especially right along the coast.
But they do eventually weaken over land, right? They can't sustain that power. Why not?
Correct. They lose their energy source. Two main reasons. First, no more warm ocean water to feed them that heat and moisture. Second, the land surface creates much more friction than the ocean.
Slows it down.
Yeah, it disrupts the airflow near the ground, slows the rotation. Plus, the air over land is often drier, which also helps to starve the storm.
That links back to what we saw in some other storm data, didn't it? Where moisture levels changing affected things. It's always about the water and heat.
It really is. Those are often the critical factors controlling a storm's life and intensity.
Okay, let's try to connect some more dots. Thinking back to the info on hailstorms, they mentioned tons of hail, obviously, but also strong winds, really wet conditions, thunder. How does that compare to hurricane conditions? Any overlap?
Definitely some parallels. Both involve really unstable air and powerful storm systems, and crucially, both rely on those big cumulonimbus clouds.
Right, the thunderstorm factories.
Exactly. So you get strong winds in both, though hurricane winds are typically much stronger and sustained over a much wider area. Both are very wet torrential rain in hurricanes, heavy rain often alongside hail. Thunder is common in the thunderstorms that make up both phenomena.
But the hail itself, the observations mention hailstones from pebble size up to baseballs, made of ice. That's different from hurricane rain, isn't it?
Very different, yes. Hail needs really strong updrafts within the cumulonimbus cloud to carry water droplets way up high where it's freezing cold, letting them grow into ice layers. While hurricanes have strong updrafts and ice crystals aloft, the lower parts of the storm are generally too warm for large hailstones to form and survive all the way to the ground, so primarily heavy rain.
Okay. And the data for that hailstorm mentioned peak intensity times and even areas within the storm path that weren't really affected. Do hurricanes have similar structures, variations inside?
Oh, absolutely. The eye is the perfect example, calm right in the middle. But then you have the eye wall, which is incredibly intense, and outer rain bands, which also contain heavy rain and wind, but might be separated by areas of lighter rain. So yes, definitely variations in intensity across the storm structure, just like in other complex storm systems.
What about the conditions leading up to them? The hailstorm data mentioned rising temperatures around noon, storms happening in the afternoon, high winds. Any similarities there with hurricanes?
Well, the midday temperature increase helping destabilize the air for thunderstorms is a bit different from hurricanes, which need that sustained warmth from the ocean surface over days or weeks. But hurricanes do often show cycles of intensifying, sometimes more active in the afternoon or evening, and high winds are definitely a shared feature, just on a different scale and duration.
And throughout all this, the idea of warm, moist air rising, creating those cumulonimbus clouds, that seems to be the core recipe for almost any severe weather, doesn't it?
It really is fundamental. That combination creates the instability, the upward motion you need to build those powerful storm clouds, whether they produce hail, tornadoes, or contribute to a hurricane.
And pressure changes too. Lower pressure meaning a stronger storm. That came up with hail, and hurricanes obviously have that low pressure eye. Same idea.
Exactly the same principle. Low pressure is key. The lower the pressure in the center of a hurricane, the bigger the pressure difference between the center and the outside air. That difference, the pressure gradient, is what drives the strong winds rushing inwards. It's basic atmospheric physics.
And underpinning all of it is the water cycle, right? Evaporation, condensation, precipitation, that whole engine.
Precisely. It all comes down to water changing phase, releasing or absorbing energy, driven ultimately by the sun. That cycle powers these incredible, sometimes destructive weather events.
Okay, so pulling it all together from this deep dive, it seems like the absolute must-haves for hurricane are that really warm ocean water providing heat and loads of moisture in the air. That's the fuel.
Couldn't happen without them.
And those huge cumulonimbus clouds are the engines, built with help from tiny particles like sea salt acting as condensation nuclei.
Yep, essential components.
And we've seen the whole life cycle born over warm water, potentially growing incredibly powerful and then fading out when they hit land and lose that energy source.
That's a great summary. We've traced how seemingly simple processes, warm, wet air rising, can cascade into these incredibly complex and powerful systems.
So it leaves me with this one big thought.
Hmm.
Given how critical those warm ocean temperatures are, how might changes we're seeing in global ocean temperatures affect how many hurricanes we get or how strong they become in the future?
That is the crucial question, isn't it?
Yeah.
And it really highlights how interconnected everything is. The oceans, the atmosphere, our climate. It's something climate scientists and meteorologists are intensely focused on right now, and definitely worth digging into more if you're curious about where our weather might be heading.